The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu. and I'll respond as soon as I can. All right, today, eventually, we're going to go on and take a look at section 11.5, part 1. We'll spend 2 days on that. But first of all, I had a couple of requests through email for, this is from 11.4, number 2. And it says, fill in the blank. And it says log base 6 of 6 to the x power equals what? Well, log base 6 of 6 to the x power equals some number, right? Let's call it box. So then we've got an exponential, a logarithmic equation. If we rewrote this as an exponential equation, we'd have 6 to the box equals 6 to the x power. Since the bases are the same, the exponents must be the same. Therefore, the box equals x. So the final answer is just x. Okay, let's see here. Now coming up is number 24. So this is 11.4, number 24. It says solve for x. And we have log base 27 of 9 equals x. So this is a logarithmic equation. Writing it in exponential form, we would have 27 to the x power equals 9. Well, if I could take this equation, 27 to the x power equals 9, and get the same base on both sides of the equation, then the exponent would be equal. This one's a little bit tricky, but what I can do, I can take 9 and write it as 3 squared. I can take 27 and write it as 3 cubed. I'm going to do this. I'm going to say 27 is 3 cubed, right? So 27 to the x power would be 3 cubed to the x power. We're not quite there yet. But now look at this. We have a power raised to a power. So 3 to the 3 power to the x power, we'd multiply the exponents and we'd get 3 to the 3x power equals 3 squared. So now we have an equation with the same base. Therefore, the exponents are equal. 3x equals 2, divide by 3, x equals 2/3. So log base 27 of 9 equals 2/3. Final answer, 2/3. Okay, before we go on, any questions from any of you? All right, then we shall proceed. And we're going to take a look at section 11.5, part 1. All right, now, yesterday we talked about log base 10 and the fact that it was used quite often. It was called common log, and the notation for log base 10 is just to write log, and on your calculator, there's a button that says log, which is log base 10, and the second function of it is 10 to the x power. Today, we're going to look at a different base, and that is the number e. Now, e, even though it's a letter, so it looks like a variable, represents a real, irrational number. Think of it this way. Pi is approximately 3.14, right? Pi is used whenever you're dealing with circles, circumference, area of a circle or a sphere, something like that. E is approximately 2.71828. E is used whenever you're dealing with something that is growing or decaying continuously. Now, what do I mean by continuously? Well, let's take the compound interest formula that we looked at yesterday. And K stood for the number of times that the interest was compounded. If it was annually, K was 1, semi-annually, K was 2, quarterly, K was 4, monthly, K was 12, daily, K was 365. You could get even more ridiculous and say hourly and minutely and secondly. Secondly, is that a word? But what if it was continuous? And why would something be continuous? Well, think of a population. Let's take the population of Yakima County. All right. I have no idea what it is, but over the course of a year, if you look in the newspaper, every day there's birth notices and death notices, right? So it's not like nothing happens up until December 31st, and all of a sudden a whole bunch of people are born and a whole bunch of people will die, and boom, the population changes. No, it's happening all the time. So we think of it as happening continuously. So a population is growing or decaying continuously. When that's the case, we use E. E is involved in that formula. All right. So E is connected with continuous growth or decay, like pi is connected with circles. Pi is a little more than 3. E is a little less than 3, approximately 2.7. Okay. Now, where can we access E on our calculator? Recall I said log, the second function was 10 to the x. There is a button that says ln, which stands for natural log. And we will be looking at that eventually here. But the second function is e to the x. So let's say I want to just get plain old e on my calculator. I'm going to push the second function key. Then I'm going to push the ln button. Let's try that again. Second function, ln. When I do that, I get e, and then the little caret power key parentheses. I want just plain old e, so I'm going to put 1 in there and close it up. When I do that, I get 2.718281828. Now, I need to be careful because it looks like there's a block of digits that are repeating. However, if my calculator had placeholders going past what 9 digits, I'd see that this number here, well, there isn't a repeating after that. So basically, we'll think of that as being E, or even more approximately 2.7-ish, okay? Depending on how far we're going to round. If I want to get E squared, I'll go through all of this and put a 2 in there. E cubed, a 3, etc. Okay. Now, we're going to look at a graph of f of x equals e to the x power. And let's go down. Let's see. Actually, I want to go up here. And we'll look at this. Okay. So f of x equals e to the x power. Again, I'm going to graph, or at least calculate, points going with x values from -3 to +3. And I'm going to round off to the nearest 10th, or maybe the nearest 100th, depending, but my graph isn't going to be super accurate anyway. So f of -3 would be e to the -3 power. So on my calculator, second ln e to the -3, close it up, and I get 0.049, we'll call it 0.05, okay? F to the f of -2, e to the -2 power is 0.135. So how about 0.14? E to the -1 power, 0.367, so 0.37. So I'm rounding to the nearest hundredth in each case. E to the 0 power is 1. E to the 1 power is 2.718, so 2.72. E squared is 7.389, so 7.39. And E cubed is 20.09. Okay, now, obviously I'm not going to graph this point, okay? Probably not even graph that point. But again, I just wanted you to get a feel for how you would plot those points. When when x is -3, y is 0.05, so that's right about there. When x is -2, we're at 0.14, so that's up a little further. When x is -1, we're at 0.37. When x is 0, y is 1. When x is 1, y is 2.72. When x is 2, y is 7, which is up off the graph. So, anyway, so we get a graph like that. It looks very much like if we graphed y equals 2 to the x and then y equals 3 to the x. Because this is 2.7-ish, it would lie in between those two graphs. All right. So again, E is not a variable. It stands for the irrational number, which is approximately 2.7. Any questions about that? Okay. Now, we're going to look at a formula, and it's sort of the continuous version of the compound interest formula. In other words, when things are happening continuously, and it looks like this: A equals P times E to the RT power. All right. So P is the initial amount. R is the annual interest rate or growth rate or decay rate. T is time, and E is just that, it's E. It says, find A using this formula, given the following values of P, R, and T. Round to the nearest hundredth. So if P is 5,000, R is 8%, and T is 20 years. First of all, we're going to convert 8% into a decimal, a non-percent number. So A equals 5,000 times E to the 0.08 times 20 power. Now, I can predetermine 0.08 times 20, or I can just put parentheses around the product and do it all at once. So 5,000, and then to get E, I'm going to go second, ln, so I've got this 5,000 E to the parentheses, I'll put 0.08 times 20, close it up, and push equals, and I get 24765.16212. And it said round to the nearest hundredth, which would be here. The 2 would round down. So 24,765.162 Any questions about that example? Okay, let's take a look at another one. NA equals PE to the RT. I like to think of this as, I don't know, there's a shampoo, used to be, that was called PERT, P-E-R-T. So this is A equals PERT, except it's not P-E-R-T, it's P times E to the RT power, but it still has the word PERT in there. Okay, in this case, P is 20,000, R is 10.5%, which is 0.105, and T is 50 years. So A equals 20,000 times E to the 0.105 times 50. 20,000. Second, E to the 0.105 times 50, close it up. 3811325.369, and the 6 is in the hundredths place. The 9 would round up, so 3811325.37. 3,811,325.37. Any questions on that? All right, let's take a look at another example. Again, using A equals PE to the RT. In this case, P is 15,895. R is negative 2%, which would be negative 0.02, and T is 16 years. So now R, the interest rate or the growth rate, is actually negative. So this population is decaying. It's shrinking at a rate of 2% per year. So A equals 15,895 times E to the parentheses negative 0.02 times 16. 15,895 times E to the negative 0.02 times 16. And I'm getting 11,542.13894. This is the hundredth place. The 8 would round up, so 11,542.14. 11,542.14. Any questions on that? All right. Next, it says evaluate each expression without using a calculator. Okay, we've got ln e to the fifth. Okay, now recall from before, log base 10 is written log, log base e is written ln, which stands for natural log. Okay, now because base e is used a lot, but they've already got base 10 as you know, taking away the exponent, or excuse me, the base. So now log base e, they write it as ln. I don't know why it isn't nl, but maybe it's log naturel or something. I don't know. But anyway, so whereas this is equal to log base 10, this is equal to log base e. Notice again on your calculator that the second function of ln is e to the x. So that will help you remember that ln stands for natural log because it's e, so log base e. All right, so now back to the problem at hand. Well, this is equal to something, we'll just call it a box. Recall from what I just said that ln is log base e. So the natural log of e to the fifth is log base e of e to the fifth. Okay, so log base e of e to the fifth equals some unknown. But if we take this logarithmic equation and convert it to an exponential equation, we get e to the box equals e to the fifth. Now we have an equation where the bases are the same, so the exponents are the same. So the box equals 5. So the natural log of e to the fifth power is 5. Okay, how about this one? The natural log of e to the sixth. Well, if you guessed 6, you're correct. But let's do it the long way, just to make sure. So this is log base e of e to the sixth equals box. E to the box equals e to the sixth. The box equals 6. Okay. How about this one? The natural log of 1 over e cubed. Well, that's equal to some unknown. So now we've got log base e of 1 over e cubed equals the box. So e to the box equals 1 over e cubed. But I could write 1 over e cubed as e to the negative 3 power. Now, we're used to having something with a negative exponent and rewriting it by putting it on the other side of the fraction bar to making it a positive exponent. Here, I want e to some power, not 1 over e to some power. So in fact, I'm rewriting it with a negative exponent, but the box equals negative 3. So the natural log of 1 over e cubed equals negative 3. And how about this one? The natural log of the fourth root of e cubed. Well, that's equal to something. We don't know what yet. So log base e of the fourth root of e cubed equals box. E to the box equals the fourth root of e cubed. E to the box equals e to the 3/4 power, right? I can convert that into 3/4 for the exponent, so the box equals 3/4. Any questions there? All righty. This says, use a calculator to evaluate each expression if possible. Express all answers to 4 decimal places. So we've got the natural log of 35.15. So on the calculator, I'm going to push the natural log button, and I get that. I'm going to put 35.15 in there. Close it up and push equals. I get 3.5596244618, but it said 4 decimal places. So right there, the 2 would round down. So 3.5596. Okay. How about the natural log of 2.7? So natural log of 2.7, I'm getting 0.993251773. That's 4 places. The 5 would round up, so 0.9933. And then how about this one? The natural log of -10. So natural log -10. It says domain error. Why is that? Recall that the base has to be positive, but not equal to 1. The thing we're taking the log of has to be positive. The resulting answer can be any real number, but we can't take the natural log or the common log of a negative number. So domain error, can't do it. Okay. Textbook calls it undefined. I don't know that I would call it that, but in any event, you can't do it. All right, now, solve each equation, express all answers to 4 decimal places. The natural log of x equals 1.4023. Recall, natural log is log base e. So this is log base e of x equals 1.4023. I know it seems kind of silly. Why do they write ln? Why don't they just write log base e? It doesn't save all that much writing. This is true in just about any subject where within the subject they have their own shortcut notation. And so if you're learning about the subject, you have to learn the shortcut notation and get used to it. All right. So log base e of x equals 1.4023. If I rewrite that as an exponential equation, I get e to the 1.4023 equals x. So it said express all answers to 4 decimal places. So I've got e, so I'm going to go second ln. So I get e to the, and then here I'm going to put 1.4023. Close it up and push equals 4.0645376661. But again, it said 4 decimal places, so that's right there. The 3 rounds down. 4.0645 would be the answer. Okay. And how about this one? The natural log of x equals negative 0.28. So log base e of x equals negative 0.28. Changing this logarithmic equation into an exponential equation, e to the negative 0.28 power equals x. And on the calculator, let's see here, e to the negative 0.28 power, I'm getting 0.7557833741. This is the 4th decimal place. The 8 rounds up, 0.755758. All right, well, that concludes part 1 of section 11.5. So let me go ahead and stop the recording.